Alright, welcome back. In this video we're going to take a look not at vertical springs but horizontal springs instead. And these are almost easier because now you don't have to deal with gravitational potential energy. We're simply dealing with kinetic and elastic potential energy. So, horizontal springs. I'm going to again draw three different positions, and it's going to be our idea that this is one system that's oscillating between all these positions. So then again, we're assuming that there's no damping, so there's no friction involved or anything. So here's going to be position A. We're going to have position B. This is going to be our equilibrium position. And we're going to have position C. There we go. All right. And again, like I said, all three of these, this system is oscillating between all three of these states. So for example, perhaps to get this started, we have this mass on a spring. We compress the spring in towards position A, then we let it go. It moves through position B to position C. That's where it turns around, goes back to B to A. And we're assuming that this happens forever. There is no damping. This doesn't ever come to rest. Since there's no damping, we can assume that the total energy stays the same, ET equals ET. And we're going to do the same thing. We're just going to take a look at how all the different quantities associated with this motion are changing over time. So we're going to list them out. And actually, I'm going to write all of them out right now. So A, B, and C. We're going to look at the position X. We're going to look at the velocity. We're going to look at the acceleration, the kinetic energy, the elastic potential energy, and the force. Let's just separate these so that they're clear for us. X, V, A, K, US, and F. I know I'm running out of room here, but that's fine. X, V, A, K, US, and F. Okay. Alright, so hopefully you can see those okay. So let's start with position A. I think that we could say, let's take the equilibrium position, and again, remember, coordinate system, it doesn't matter where you set the 0 to be, but let's set our 0, or our position 0 to be at equilibrium. That means, what we're talking about here for equilibrium is we mean the unstretched length of the spring. And notice that's a little bit different from the equilibrium over here. Here, equilibrium was where the forces were balanced, and I guess the forces are still balanced over here, but in this case, the forces being balanced means that the spring is not stretched at all. Whereas here, in equilibrium, because we have to balance that downward gravitational force with something, and that something happens to be the spring force, our equilibrium position made it so that the spring was stretched. Here, the spring is definitely stretched, or is definitely not stretched, but we're still calling, but that is also the equilibrium because we don't need the spring to balance the downward force of gravity. We have the normal force to do that here. So let's call this 0, the initial position, and let's go back to A for a second. Let's call this a negative, the negative maximum position. And that means that the X down here must be at the positive max, the farthest it goes to the right in the positive direction. At the release point A, we know that since it's the release point, the object hasn't started moving yet, so the velocity must be 0. So it's 0 at this turning point or release point. And that also means, since the velocity is 0, the kinetic energy must be 0 as well. The acceleration for point A. Okay, if we have compressed the spring at point A, there's only three forces on this object that is moving back and forth on the spring. There's a normal force up from the surface, there's a force of gravity down from the earth on the block, and there's also the spring pushing to the right on this block. And that means that the net force on this object is going to be positive and to the right, which also, and it's also going to be at a maximum because this is the farthest that the spring compresses. So not only is the force at a positive maximum. But that means, because of Newton's second law, F net equals ma, that the acceleration is also at a positive maximum. And then the last thing that we have to fill in is the elastic potential energy. Well, because this is the maximum compression of the spring, that means we're storing all this energy as elastic potential energy. So US is at a max. Moving to B, the equilibrium position for B, we see that this is where there is no, the spring is at its equilibrium length, it's at its unstretched length, okay? So what that means is that there is no elastic potential energy, so this is 0. Since we're only dealing with two different types of energy here, we're not dealing with friction, and this object isn't moving up and down, so there's no gravitational potential energy. That means all the energy must now be at in kinetic energy. So that is now at a maximum. And if the kinetic energy is at a maximum, then the velocity must also be at a maximum. Okay, so the velocity is at a maximum at the equilibrium position. And I think you'll see that's a recurring pattern as we go on. Since we're at equilibrium, that means the forces are balanced. There is no spring force anymore, and there was no friction in the first place. There's only a force of gravity down from the Earth on the block, and there's a normal force on the block from the table. Those two forces are balanced. We're not accelerating in the y direction at all. We're not even concerned with the y direction. And there are no forces in the x direction, which means that the net force is 0, which means the acceleration is 0. Which makes sense, because if the velocity is at a maximum, that means that the object is not speeding up anymore. As soon as this object starts to move towards C, we're going to have a backwards force on it towards the left. We're going to have something slowing down. The velocity is becoming less and less. C is the other turning point. This is when the spring is as stretched out as it can possibly be. Since it's as stretched out as it can possibly be, it's ultimately just about to start moving back to the left. And since it's moving back to the left, or just about to start moving back to the left, we can say this is a turning point. This is where it has no speed. It's gone as far as it can to the right. It's about to turn back to the left, but it hasn't started moving that way yet. So no velocity. Since there's no velocity, there's no kinetic energy. And since there's no kinetic energy and all that energy has to be conserved, it has to go somewhere, the elastic potential energy is at another maxima. Okay, there must be another maximum here. And that is because the spring is as stretched out as it's going to be. Since the spring is as stretched out as it's going to be, the net force is directed back to the left, and that force is given by the spring force. There's nothing to oppose it, so the force is negative and at a maximum, as is, because of Newton's second law, the acceleration, negative and at a max. Okay? So again, these are things that you should be able to think of when you see a spring system oscillating. You should be able to identify certain points where different quantities are at maxima and at minima. And the more you see them, the more that this will be easy for you. So what I want to talk about now is what factors could affect the period of oscillation. Remember, period is the amount of time for one complete oscillation or cycle to happen for a mass and spring system. One complete oscillation is not going from A down to C in either of these cases. It is going from A all the way through to C and then back up to A. That is one complete cycle. A all the way to C and back up to A. Or alternatively, C up to A and then back to C. C up to A and then back to C. Or you could even say from B to C, back to B, that's only half a cycle, up to A and then back to B. Until the motion starts over. Okay, that's what one period is. So we want to know what sort of factors could affect the period of oscillation for the spring system. Some common ideas are that possibly the mass could affect the spring system. You might have maybe having a more massive spring will change how quickly this goes through its cycle. The spring itself, the spring constant, how stiff that spring is, that might have an effect. People sometimes think that does something. Or perhaps the initial displacement, how far you pull or compress that spring in, like, say, position A, or if you took this from its equilibrium spot and pulled it down to C, that initial displacement, perhaps that has something to do with it. So I'm actually not going to tell you this. We're going to work this out in class for ourselves, either through an experiment or a simulation. So we will get to a point where we have an equation here, but we're not going to talk about it just yet. Okay? So we're going to save that for an in-class demonstration. In the next video, we're going to talk about pendulums, so let me set that one up and then I'll be right back.